Okay, good. So we have Shankha Chakrabarty from INF in Torino, and he'll tell us about classical versus quantum field treatments of axions. Over to you, Shankha.
Thank you. Just to make sure, can you see the full slide for the presentation, or you're seeing only partial slide?
We're seeing the first slide of your presentation, including the title and the footer and your name and affiliation.
Okay, that's great. So everything's working fine. Okay, great. So good morning, everyone, and greetings from Italy. So I'll be talking about classical versus quantum field treatments of axions. So QCD axions, or axion-like particles, are highly motivated candidates for cold dark matter. The most interesting feature which distinguishes this kind of candidates from other candidates of cold dark matter is that they have very high degeneracy in the phase space. For example, for QCD axions with mass of order microelectron volt, the phase space degeneracy is order of 10 to the 61. And this number is constant in the cosmological timescale because the number density reduces like 1 over a cube, and also the momentum decreases like 1 over a. So keeping the whole this degeneracy constant as a function of cosmic time. Now, another way to look at this is the following, that this is also similar to the total number of axions within a de Broglie volume. Now, since there are so many axions and the wave function of individual axion overlaps with each other, usually in cosmology or in the context of structure formation after the axion mass is generated, they are treated like classical fields. Now, the classical field description may describe certain phenomena. However, they are not accurate in all the aspects, especially in the context of thermalization. Because if we start with some arbitrary distribution of axions and let them evolve following classical field theory, we end up getting a Maxwell-Boltzmann distribution, which do have this intrinsic ultraviolet catastrophe. But starting from the same initial distribution, if we follow the quantum field evolution, we end up with a Bose-Einstein distribution. So there must be a time scale after which the quantum evolution will differ from the classical prediction. Now, we are interested to find out this time scale. So at this point, probably I should also mention that this enormous degeneracy is not very familiar with what we know in the laboratory, like superfluid or other bosonic systems. And it is also very challenging. It's formidable in terms of n-body calculations, like n-body simulations, and it is also challenging from theoretical perspectives. But we made some progress to see through what makes the quantum field calculations different from the classical field calculation. So first, I will explain a formalism that we have developed in this work with Inomoto, Han, Sekivi, and Todarello to calculate this time scale. We refer to it by duration of classicality. And then I will show you some examples where we applied this formalism and explain what we got. Since we are interested in the cold dark matter, we go to the non-relativistic regime when the real scalar field phi is replaced by a complex scalar field, and the Klein-Gordon equation reduces to a Schrodinger-like equation. It's important to note that this is not exactly a Schrodinger equation, and it has a different name in the literature. It's called Gross-Pitevsky equation, because of this fact that the potential term is nonlinear. So it depends upon the field itself. In the classical field regime, we replace the quantum field psi by a complex wave function. However, in the quantum field treatment, we must treat the field as an operator and maintain these commutation relations. Now, in the classical field treatment, we can write down the complex wave function in terms of a magnitude A and a phase beta. And it's found that we can define a number density and velocity field out of this magnitude and the phase, and in terms of the mass also. And if we replace this complex wave function back to the Gross-Pityevsky equation, we find that these axions behave like a classical fluid, except one term. So you get back continuity equation, and another equation is the Euler-like equation, which differs from the classical fluid by this one term, the last one, which is called quantum pressure. It just represents the tendency for the wave packets to expand. In the quantum field treatment, we expand the field in terms of a set of complete orthonormal functions and the corresponding annihilation operators. But at this point, probably it's also worth mentioning that typically in the literature of axions, or especially in the cosmological context, we take the UKs as the momentum eigenstates, like e to the ikx. But of course, in the most general way, it could be anything, provided they are orthonormal and they form a complete set. So, since we are interested to study the difference between the classical solution and the quantum field solution, we construct this orthonormal complete set in a specific way, in such a way that the classical solution psi, which is the solution for the Gross-Pityevsky equation, is a specific mode of the quantum field. So we construct this set of UK when k goes to 0, U naught, like U0, is similar to the complex wave function, which is the classical solution. So UKs are similar to the classical solution, but they differ by some long wavelength modulation. This cartoon is just for some intuitive understanding. So this bold red line represents the classical solution, and all these wiggly lines represents the wave function similar to the classical solution, but slightly different. And here, this chi is not exactly the physical position, but it is we call it a co-moving coordinate. It is constructed in such a way that the density of the axions in this new space, in chi space, is constant in both time and also with position. Now, if the mode corresponding to k equal to 0, which is the classical solution, is highly occupied, then quantum corrections are found to be suppressed by 1 over n. So one can describe the fluid without taking quantum field theory. But the question is, when the system evolves and they do have self-interaction, do the quanta stay in that mode or not? And we will answer this question negatively for all the examples we have studied so far. Now, if the quanta leave the k equal to 0 state, then we can calculate what is the total number of particles that have left the k equal to 0 state after some time t. And we define duration of classicality, that is the time scale after which classical theory becomes invalid, is the time scale when almost all the particles that have evaporated from the k equal to 0 state. So when like NeV, T classical is almost equal to the total number of particles. So we have studied 3 examples. The first 2 are for self-interactions, attractive self-interactions. The first one is attractive lambda phi 4, the simplest one. And then we studied gravitational self-interactions. And the last one is repulsive lambda phi 4 interactions. The last example may not be directly related to the physics of axions. However, I will explain why it is important to consider this, and it gives us very important insights about the quantum field treatment and why it differs from the classical field treatment. So, for attractive lambda phi 4, we take the homogeneous solution of the classical field equations. So N naught is the number density, which is constant, and there is it has a modulation time with some frequency delta omega, which depends upon the strength of the self interactions. The important point is, in the classical field equation, this homogeneous solution persists with time. So the condensate, if it starts with homogeneous initial condition, it remains homogeneous. But when we do quantum field treatment, starting with the same initial condition, we find out that there is an instability, which is the quanta from k equal to 0 mode jump out in pairs, and all the modes with wave vector less than some cutoff value become populated. And also, for modes with those wave vector which are unstable, the occupation number grows exponentially with time. So this gamma k is the rate of exponential increment. So you can see that when k is less than kj, gamma k is real, and we get this instability. But for modes with k larger than kj, gamma k is imaginary and they do not grow. I mean, they appear, but they oscillate. And we find out the time scale after which almost all the quanta leave the mode corresponding to k equal to 0, which is the duration of classicality. After this time, the classical solution is invalid. And that time scale is inversely proportional to the strength of the self-interaction. We study, or we do the similar set of calculations for the gravitational self-interactions, and we did the calculations for a matter-dominated expanding universe. And again, we started with the homogeneous condensate. In the classical field treatment, the homogeneous condensate persists in time. But in the quantum field treatment, we find out similar set of instability. So again, the quanta jump out of k equal to 0 mode in pairs, and the modes with wave vector less than some cutoff value become populated. Interestingly, it turns out that this cutoff wave vector is the same as the Jeans wave vector. Now, the reason behind this instability is the following. It is similar to the Jeans instability in astrophysics, because when you have the long wavelength mode, that is the modes with wavelength larger than kj inverse, then attractive force of gravity dominate. And that's why they're unstable. But for the modes with shorter wavelength, the quantum pressure dominates, and that's why they do not undergo this kind of instabilities, because sort of the quantum pressure balances out the attractive nature of gravity. And here also we find out the time scale after which the classical solution is no longer valid. That means the k equal to 0 mode is entirely depleted. And this is also inversely proportional to gm square, which is the strength of self-gravitational coupling. Now, the reason in these cases why the classical field equation is differing so much from the quantum field calculation is the following. In all these examples, we started with homogeneous condensate. Now, in the classical field theory, when you start with homogeneous condensate, you do not have any other density perturbation. So it behaves like the you are sitting on the top of an inverted harmonic oscillator. So whenever you get a gentle push, it just rolls down either side. The fact that classically you do not have any fluctuations, it does not grow. But in the quantum field treatment, the quantum fluctuations are intrinsic. And because of this attractive nature of these self-interactions, all these quantum fluctuations grow, and the regions which are crowded already become more crowded. So this is the underlying physics why in quantum theory we do have the instability, but in the classical theory in these cases we do not have. Now the question arises, what happens if you do not have attractive self-interactions, but you have repulsive self-interactions? Do we expect the classical theory to differ from the quantum theory? So to understand this quantum phenomena in a much better way, we did this set of calculation for another system with repulsive lambda phi 4 interactions. So for the repulsive lambda phi 4 interactions, in the classical theory, the density perturbations, at least in the first order density perturbations, the modes are stable and they oscillate with some angular frequency. So here, just to point out, okay, these S Ks are equivalent to the density perturbation in mode K, and they oscillate with some frequency omega K. To study the difference between quantum and classical evolution, we consider again here a simpler case where we have the homogeneous background corresponding to K equal to 0. And we have one specific mode with K equal to P. In the classical theory, in the first order density perturbation, we find that only the mode with K equal to P is present, and it oscillates with the frequency that we expected, omega P. If we do a second order perturbation theory in classical field theory, we find that modes with K equal to twice P appears, and they also oscillates, but the amplitude of oscillations is suppressed by one factor of density perturbation. In fact, even if we do the classical field theory for all the, like for all order, like generically, we find that for this specific example where you have K equal to 0 and P initially, you will get only modes with K equal to P, twice P, thrice P, and so forth. And all the modes, the occupation number in all the modes, they just oscillates. However, when you do quantum field calculation, we find that there is one specific scattering process among the quasi particles which leads to instability. The process is the following. K equal to 0, P goes to K and P minus K. And the modes with this energy difference, which is omega K, omega P minus K minus omega P. So omega 0 is 0, so it doesn't appear here. So the modes with K such that epsilon is almost 0 have the instability. And for those modes, occupation number grows exponentially. So this is the occupation number, and this is the rate of exponential increment. And we find that there is some tolerance that epsilon must be less than this factor. So Q was found to be some complicated function, which I'm not mentioning here. Delta omega is the natural frequency associated to this coupling strength, the density, and the mass. And delta n over n naught is associated to the amount of inhomogeneity that you already have, or you start with. So there is a...
Would you finish in about 5 more minutes so that we have some time for questions?
Sure.
Okay, excellent.
So we do have the window of instability here. So this is just to represent the window of instability. Here we plot the ratio of K over P. The mode P was originally occupied. And cosine phi is the angle between K and P. So there is only in this regime where the modes lie which are unstable. Now, this is the summary here that you start with 0 and P, and this is the quantum field theory where the scattering process is occurring. And here also we find out the duration of classicality. The important thing to note here that here the duration of classicality is inversely proportional to lambda, the self-coupling strength, and also the amount of inhomogeneity that we started with. Now the question is why this kind of phenomena, this kind of scattering process was not happening in the classical theory, but it is happening in the quantum field theory. The reason is, let's consider a process I, J going to K and L. In that case, the rate of change of one of the final state occupation number is given by this expression in the classical field theory. And in the quantum field theory, when you treat when you include that they are bosonic quantum fields, we get some correction to this classical result, which are represented by all this +1 here. So when both of the final states are unoccupied, when nk and nl are 0, this expression is 0. That's why in the classical field regime, when both of the final states are empty, the scattering process is not allowed. But this is not the case in the quantum field calculation, because even if both nk and nl are 0, the first term contributes. So this is the reason why this scattering process does not appear in the classical field theory. To summarize, okay, we are interested to find out the difference between quantum field calculation and the classical field calculation. And we have done some, we have developed a formalism where we treat the classical solution as a single mode of the quantum field. If only this mode is highly occupied, the classical description is accurate and the quantum description and the quantum corrections are suppressed. However, we found that in all the examples we have studied, that mode is not stable when the system evolves and when the system do have self-interactions. So we have studied both attractive lambda phi 4 and gravitational self-interactions. And we find out that certain modes with wave vector less than a cutoff wave vector are unstable and they become populated. Also, for the repulsive lambda phi 4 interactions, we found that the classical and quantum theories predict different results. The underlying physics that was common in all these cases is that certain single particle states that are not occupied in the classical field theory do get occupied in the quantum field treatment. And they can play an important role in the self-interactions, because when we represent all these overlapping, all the axions with overlapping wave function by a single classical wave function, we do not provide enough room for them to self-interact or to study the transition between several single particle states. However, these kind of transitions are found to be important in the context of thermalization. So in the context of thermalization, it seems that it is required to treat axions as the quantum field, unlike the way it is treated in most of the recent works in the context of thermalization. Thank you.
Okay, thank you, Shankha. We have time for a couple of questions. So I'll go over them one by looking at the chat box.
Okay.
Okay. The first question was from Raghu. He asks, why in the classical approach, the 5-4 interaction and you start with a homogeneous mode? Is there no loss of homogeneity since 5-4 will allow for mode mixing?
Okay, so we consider this homogeneous condensate, which is the initial condition, and it was the simplest to calculate analytically. But in the classical cases, no, it is stable. As I explained, it is like the homogeneous condensate remains homogeneous. But to get this kind of instability in the lambda 5-4, you have to start. And if you want to do classical theory in lambda 5-4, you have to start with the homogeneous condensate plus some inhomogeneity, because in the classical case, it will not have some intrinsic quantum fluctuations. You have to put them by hand.
So actually, I had a related question right after that, which is
Okay.
that so if we are interested in the real world where axions, we are interested in whether or not the axions remain coherent. So there are two sources of instability, the seeds for the instability, right?
Yes.
One is that there are quantum fluctuations, which is what you have looked at.
Yes.
The other would be that, we live in a noisy, bubbling
Exactly.
universe.
Exactly.
And already classically there are perturbations. Do you
Yes,
have some sort of intuition which one will dominate?
Okay, so great. Thank you for this. So here, because, okay, all these examples that I have shown here are based on like robust analytical results. So here, well, when you have this very chaotic system, at some point you have to resort to some kind of intuitive arguments and to find out some time scale, some approximation. Okay, so here we have considered only the effect of self-gravity. However, in real world, as you mentioned, there are some external fields. And here we are starting with a homogeneous condensate. And we do have only self-gravity. But in the real world, even if you start with homogeneous condensate, they will soon become inhomogeneous because of the external fields. And soon they will go into a regime where our calculations will not be valid. So that's the reason, based on this calculation, I cannot give the correct time scale for the real axions. So what we have to do that, we have to start with some initial condition where we have to have the inhomogeneity, which may represent the inhomogeneity that might be caused by other thing. But the system very soon goes to nonlinear regime, and it's very difficult to do the analytical calculation at that point. And I have no idea how to do this kind of quantum field treatments in a simulation. So it's
okay. So next question is from Koushik Dutta. He's asking, in standard free QFT, classical Klein-Gordon equation is same as quantum version using Heisenberg equation of motion. Each K mode is simple harmonic oscillator. For your case, it is not. Is it due to interactions or occupation number problem?
Okay, so when you have a free classical theory, like free quantum field, let's say, and no self-interactions, you do get the quantum field results without doing quantum field theory. Let's say, I think what he's saying is right. We agree with that, because when we have only the dispersion relation, which is like k square over 2m, you can actually you can represent the quantum field by the classical theory in the non-relativistic regime. So yes, in our case, it's because of the self-interactions that we are having.
So the difference is due to self-interactions.
Yes.
There is then a comment by Patrick, and he's saying nice talk, and they refer to some related work that they have done, and he will speak about it today. So I think that's good information. Please do attend Professor Dasgupta's talk.
Okay, surely. And yes. Thank you.
There is another short comment by Shiladitya Pure. He's asking, could you please say why axions jump in pairs?
Okay, because it's a scattering process like between 4 states. So you have 2 initial quasi-particles, like let's say they are starting with like Ki and Kj, and then they scatter with each other and goes to 2 final states.
No, I think he's asking about your initial point where you start with just pure vacuum and you go into 2 states, and there have to be at least 2. So my guess was that this is because of momentum conservation. Is that wrong or?
Okay, yes, that's also true. But if you, let's say, if you do study the scattering process of, let's say, lambda phi 6 or something like that,
I see. Yeah. Okay.
then it might be a different phenomenon.
Sure. Okay. Then there is maybe a couple of more questions. Okay, lots of questions, but let's take them because I think it's okay. So can you comment on the paper by Mark Hertzberg with the title "Quantum and Classical Behavior in Interacting Bosonic Systems," where they claim that for high occupancy number, quantum and classical results are equivalent.
Okay, but I am not very sure how the self interactions was treated. I'm not very sure whether the self interactions was treated correctly in that paper. So, and I have not done that work. So this would be my preliminary reaction.
Okay, so there are 2 more questions. Let's see if there are quick answers. If not, we should cut the discussion short and move for lunch. So the first question is again from Rangarajan. He's asking, what are the differences for axion dark matter in terms of observations for the classical approach and the quantum approach?
Okay, so I can give some quick examples about here. Okay, now in the whole idea of studying this set of systems was behind the fact that whether these axions do form the Bose-Einstein condensate or not. Now, all these existing literatures, in some of the existing literatures, they study the whole thing in a classical theory and using Gross-Pitevsky equation, and they seem to find different results from the intuitive quantum field arguments. Now, if the axions do follow this quantum field treatment and do form this Bose-Einstein condensate, it affects certain things. Number one, it affects the velocity field and the density, number density within the galactic halo. For example, you cannot have caustic rings unless they fall in with some rotational modes. And these kind of rotational modes are not easy to find in the classical field theory because the rotational modes, they just decay. But if they form this Bose-Einstein condensate, these rotational modes appear spontaneously because of this spontaneous vorticity. So all this tidal torquing and all the angular, all this tidal torquing and other torque that gives this angular momentum, they convert all this angular momentum into vorticity, and that's very natural phenomenon, and that has been observed for, let's say, in laboratory for superfluids or other similar cases. But in case of axions, they will form only if they form Bose-Einstein condensate. So in that case, yes, we have a very observationally different results.
The last question, this is from Swagat. He's asking, during the oscillations of an axionic field, due to phi-4 interaction, wouldn't there be parametric self-resonance like we have during reheating?
I think what you mean by parametric self-resonance is probably what I am also describing. That's what I think. I don't know.
I think you're right.
Yes.
Okay, so that were all the questions. So we will close the session at this point. Thanks to all the organizers. Thanks to Shubhendra Mohanty, who gave the first talk. Thanks to Shankho, who gave the second talk. And thanks to all of you in the audience for wonderful questions and fantastic participation. So I call the session to a close.
All right. Thank you.
Thank you.
Over to you, Subinoy or Raghu, whoever is there.
Yeah, so I think nothing to say. We will meet at 2:30. Yeah.
Actually, Shankho is still around. Can I
Yes.
ask a couple of more questions, Shankho? Sorry, I'm a bit interested in what you've done.
Yeah, sure.
I know that the AV team probably has to shut down the live stream very soon, so we'll not take too much time. But just a very quick question. So,
Sure.
again, coming back to this quantum versus classical perturbations.
Yes.
So, I know what you're saying is completely right, that doing this inhomogeneous starting conditions with quantum fluctuations is very hard. I mean
Yes.
that we're not going to talk about that. But
Right.
let's say we could ask, what is the comparison between time scale for quantum fluctuations to lead to break of, basically the quantum break time. What you're computing, this classicality time, is the quantum break time.
Yes.
Right. And this is, you are computing just purely from quantum field theory fluctuations.
Right.
And the other thing that could be done is just ask, what is the time scale for classical fluid perturbations to lead to instabilities? Just forget about quantum physics completely.
Yes.
And which of these time scales dominates?
I think you're right. So, okay, so there have been some numerical studies.
I mean to look at, for example, the paper by Guth, the Chanda Prescott Weinstein, Guth, and
Yes.
Hertzberg paper. So they do a purely classical treatment, I think, right?
Yes. So
just interject here.
Yeah.
And you maybe answer it later, was related to what Basudev just said. They use Gross-Pitowski equation. Now, why do you keep referring to Gross-Pitowski equation as classical? In what sense it is? I mean, it's after all a Schrodinger equation, a non-relativistic Schrodinger equation, non-linear Schrodinger equation. So why would we think of that as classical? You can come to it later, but since Basudev mentioned classical, I just thought interject. But go ahead.
So it is classical with respect to quantum field theory, because the fact is, you have this de Broglie volume, and when you have a large number of axions, of course, the wave function for the individual axions overlap, and this is the motivation to represent all these axions within the de Broglie volume by a single complex wave function. Now, when you do that, you completely lose the identity for each of these axions. So, especially when you have self interactions, you don't have any room to study how they are undergoing the transition from one single particle state to another. And now, coming to what Professor Dasgupta was asking, so there was a numerical study in our group. In one of our collaborators actually did this simulation for starting with a number of oscillators. And she also found that when you have only classical field theory, it takes much longer time or actually the system never thermalizes.
Okay, excellent. So that's a concrete answer. You're saying that the quantum field theory fluctuation, at least in some example that has been looked at, are stronger.
Actually, this is also similar. We actually later found out that the underlying fact is the following. Let's say you have n number of particles, which you have to put in m number of states. Now, in this case, in the quantum theory, the degrees of freedom is enormous. Like you have to find out all possible combinations to put them. But the degrees of freedom in classical field theory is not that large. And that plays an important role. And actually, it was studied in, I think, late 70s or early 80s by Enrico Fermi and others when they were just... Yes?
Sankha, I'll just make a quick comment about this simulation thing that you just mentioned. Now, the paper that I just mentioned in the chat box by this Mark Hertzberg, they actually claim exactly the opposite by doing these numerical simulations. And so this is a major confusion, and probably it would be nice if you can have a look and make a comment where they are also going wrong in your understanding. I mean, they also say that we do this, the number of oscillators, and they also take the interactions, and I forgot the details at the moment.
No, they also actually what they do, they take an average over all the initial phases.
Exactly. I think this is super important. And this is the way in which the classical and quantum theory can actually, at the end, give you some the same conclusions, right? Or the same predictions. Just because you are taking this average over initial conditions that corresponds to the quantum uncertainty in the initial conditions. So, is the way
Yes, it is not very obvious though when you only do Gross-Pitarski equation in the classical way and predict something, whether that treatment is similar to or equivalent to taking the initial condition over all the initial quantum states.
No, it is not. I think you have to do many classical field theory calculations with different initial states with different phases. Yeah, that's the key. Or prove that one simulation is enough, that you don't need many. Because in some cases you are already starting with many modes with completely random phases. So in those cases probably are fine.
Yeah, so in the classical cases you have to be very, very careful whether your classical results will converge to the quantum mechanical expectation values. But yes, I think if you do it quantum field theoretically, you don't have to worry about all these things and worry about these questions of validity, let's say.
I completely agree, but the problem here is that normally it's not very easy to do the quantum field theory calculation, right? You can do it only in very few examples, which are very idealized.
Yeah, that's true.
That's why we do classical.
I agree. Yes. Yes.
Okay. Any other urgent discussions, comments, questions? If not, I will log out, and then others can continue if they are permitted by the hosts.
Yeah, we can continue, but I'm also
hungry.
Thanks, Sankha. That was really interesting.
Thanks, Sankha. That was very helpful, the talk.
Thanks,
Sankha. Thank you.
All right. Thanks, everyone. Bye.
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 Hi, Professor Rangarajan. I saw your...
Yeah. Can you still see me?
Yes.
Yeah. No, actually, Koushik, I, and a few others have been looking at Pierre's work for Sikivi's work for the last few weeks. I mean, over the years what he's been doing, and we're really just annoyed by the fact that there's so much of this conflict in the literature, and it almost seems as if people are talking past each other and not addressing each other. I mean, sometimes when I see some of those papers where they've criticized the earlier work of Sikivi, etc., they make certain comments. But if you read Pierre's papers, the same issue has been addressed there. So sometimes it's not clear whether people are misunderstanding each other or what the issue is. And maybe sometimes Pierre is not addressing, or your papers are not necessarily addressing the comment made by the other people. So we're just trying to make some sense of this. And, the Gross-Pitarski equation, if you look at Guth et al., it is, see, first of all, if you have particles overlapping each other, it's a very, with de Broglie wavelengths overlapping each other, it's a very quantum state. It's not a classical state at all. So, and you have a Gross-Pitarski equation, and if you see the way they do it, you take coefficients and you say mod square of that is the number density of particles. So to me, it's not clear that that is a classical approach. I mean, it is a field, but the traditional classical approach was where we just did phi double dot plus phi dot plus m squared phi equal to 0 and did all of that. That's not what Guth et al. Was doing. So it's not clear to me that the differences between you and them is classical versus quantum, or is it just you're doing things more quantum than them or something of that sort?
I think it's the latter. So we are actually treating it like a quantum field. We are not resorting to, we are basically considering all the modes for the field psi. But I think they start with, if I remember correctly, they start with expanding this field psi in terms of some complete set of functions. But I think at some point they go to purely classical, like in the classical field regime, if I remember correctly.
So for you, what would be the transition to the classical field regime? If you start with a Gross-Witkowski equation, what is the transition to the...
You mean Gross-Witkowski equation with a quantum field?
Well, I mean, it is the, I mean, it's IH bar d psi by dt, right? So, I mean, in a sense, it is a wave function. It's a nonlinear Schrodinger equation.
Okay, so I think it should be, I should probably mention it here that, okay, so initially you have the Klein-Gordon field, right?
Okay.
Phi.
Yeah.
So which is an operator
Okay.
in the quantum field theory.
Yeah.
And you get this Gross-Witkowski equation because you go to the non-relativistic regime.
Yeah.
So here also, since you go to the non-relativistic regime, the same operator phi is replaced by another complex field operator, which is psi.
Yeah.
Now, in my case, I will call it quantum calculation when we retain this operator identity of the field psi. The moment I will lose this operator identity and replace psi with some complex number, like complex wave function, say, I will call it classical.
It's more like quantum mechanics.
Yes, it's more like quantum mechanics, right? But not quantum field theory. Yes, that's right.
Okay, so okay.
But Raghu,
Yeah, go ahead, Koushik. I'm just trying to
just probably diverting a bit, Sankha. So, but is it the story about so this is so there is this classicality and quantum, the field theoretic treatment, and as you emphasize, this is related to the thermalization process. It may play a role, but is the issue about the structure formation, which was debated at the very early stage, like the length scale structure? You know, what is the length scale of the structure? That issue, do you think that analysis that you are doing, that means the quantum treatment is important, is crucial for any cosmological structure formation? You know, the length scale. I mean, not about this caustics, I mean, necessarily.
Yes. I know you are talking about this cosmic. Yes. As of now, I'm not very sure how important it would be. Maybe you're talking about probably the power spectrum for the very large scale, right?
That's correct.
I mean, size of the collapsed object, or the size of the BEC object, basically.
Because that was the initial claim by Guth et al. That the correlation or maybe these objects cannot be so big, where the CKV in his original paper with Young and CKV, the claim was that this length scale can be really large.
Okay. You're talking. Okay, I see. Okay, okay. I think.
And the source of this thing is again the quantum the quantum field theoretic treatment. That was the initial claim, and I'm asking whether that claim of CKV still holds, or is it that at least that part is not. Yeah.
So here the idea is the following. Okay, I think in Guth and all they talk about this they expand the field in terms of like absolute momentum eigenstate, like k equal to 0 and so forth. Like those k's are equivalent to the actual physical wave vector. The claim of CKV was that even if you have, and Guth et al., they also related the fact that the correlation length is equivalent to the length scale of homogeneity. So in Guth's paper, if I understand correctly what they mean, the correlation length is the scale of homogeneity. But what CKV's suggestion was that even if you have inhomogeneity, there might be correlation. For example, in the laboratory of where they have this condensation, it may not be homogeneous in terms of number density, but they are perfectly correlated as long as there is this single condensate. So I think there is a major point of confusion, which we wrote a section about that in our paper of 2017, but I don't know whether it cleared up anything in the literature or not.
No, in fact,
It's
Devashri Sandalia, who is a student who's working with us, and Shiladitya Pore is also in here. So ultimately, the size of the object, which is in the form of a BEC, according to Guth et al., is something like axion stars or something.
Yes, these are very small scale objects.
Small
yes.
scale. And is the claim of your group that it is large? It may have inhomogeneities within it, but it will be large. I mean,
yes. If the condensate is large, but yes, if the whole condensate is over the galactic halo size, let's say, but there might be small inhomogeneity here and there because of, but they may not lose the correlation over the entire range. The presence of inhomogeneity does not necessarily imply that there will not be any correlation.
Okay, so that's
what our understanding at this point. Yes.
Sure. Just moving away from the term correlation, does it mean therefore you can get a halo of, I mean, a galactic-sized halo, which is in the form of axions in a BEC state? I mean, that was the whole point, right?
Yes, yes.
And that will be in spite of the presence of inhomogeneities that show up.
Yes.
So is there a way of reconciling it with what Guth et al. Says, in the sense that maybe they're right that you're actually forming both axion stars and a larger halo?
Yes, that is something I have not thought much about, so I can't comment anything. But what you're saying is relevant. I think, yes, it is. I have to think about that.
Okay.
Because the other thing is also important that when we think about these axion stars or all these axion mini clusters, it's not very obvious. I know there have been some very recent works about the time scale it takes to form such small scale compact objects, you know.
Sorry, I lost power. I don't know if you all are still there.
No, yes, I am here.
Yeah. I don't know. I mean, if you want, you can repeat what you just said, or I can get it from the others. But hello.
Yes.
Yeah. So what were you just saying that I probably missed it?
Yes. Can you please remind me again?
Yeah. I think we were. So the point is, therefore, you can have. I guess you were saying that. As
people are talking about these axion stars.
Yeah, axion
it is also not very
clusters. So, do you?
Okay, so the way they have been studied so far is like as if you're solving a steady state solution for like the Gross-Pitevsky equation, but it is not very clear how long it takes to form one such object. I think there have been some very recent work, but I have not read them carefully yet. But it's not very obvious how long it takes. And if we do quantum theory, what will happen to the shape or the distribution in those objects?
No, I think Kachev has shown, I mean, in his talk itself, that you can follow your system for a while and you will see that mini clusters are forming, axion, both stars are forming, and then mini clusters form, etc. So I think those simulations exist for the time scale for generation of, in that framework, for time frame of generation of structure. So I think that's there. So the only issue that finally remains is, if they are right, then you have only bow stars and mini clusters, and you don't have this large halo, which is a BEC. Because if you all are right, then you have a huge halo, which is a BEC.
And with some small objects, yes. I'm not very sure about that.
Yeah.
Yes.
So
there's something we are. Yes.
And as you point out, only if you have a BEC on the scale of a halo can you have vortices which are generated through tidal torquing, and then you can have the caustics.
Yes.
So that's so I asked Pierre this. Maybe if you have any comment, you can share. If you look at the older papers of the group, of your group, with etc., the way the treatment is somewhat actually similar to what you all did, which is you start with some 5 or 10 states which have large occupancy.
Yes.
And then you look at, through interactions, how do states get depleted, etc. In Erken et al., they were not looking at the rate at which states get depleted. They were looking at rates for particles to move from one state to another. And that was, quote unquote, I think, some measure of the thermalization rate.
Yes.
Okay. Now, so my question is this: that how does structure formation happen if axions are the dark matter and they've become a BEC? On galactic halo scales, your mode enters the horizon, collapses. So it's a 2 megaparsec whatever scale, enters the horizon, grows, becomes nonlinear, and collapses. Okay. Now, is this density, if the axions are all in the form of BEC, the structure formation is happening when it is in that BEC state. What is the amplitude for the density perturbation on the scale of the galactic halo? The reason I ask this is that from standard inflation, you might say it is of order 10 to the minus 5, I mean, what we normally believe. But in all the, the formalism that you all have been using, you are starting with low momentum states with very high occupancy. If that translates into a density perturbation on that scale, with very high occupancy, let's say 10 states are highly occupied, and you're looking at one of those scales, which is of the order of the galactic scale, then the delta rho by rho will be 1 by 10.
Right.
1 by 10 squared or something. So then that will be very large, and then your formation of galaxies will, the structure formation on galactic scales will follow a very different evolution. So am I misunderstanding something here? I mean,
no, I think you're right, but in this quantum field calculation, it's very difficult to go to, go until that regime, because this, as we were mentioning, the whole system will soon enter into a nonlinear regime. And I don't know how to do this numerics, but maintaining this quantum field nature, I have no idea. So
no, I would just go one step before that. If the scale that is of galactic size happens to fall in your what you all call the condensed regime, that is the set of states that have high occupancy, then will not the density perturbation on that scale be very high? And would that then just give you, your system would go nonlinear very fast, and then galaxies might look a little, or galactic halos might begin to look different?
Yeah, that's actually right. There might be some effect on the distribution of dark matter in the halo. Yes. but no, we have not studied this and we have not thought about it this way. But I think it would be interesting to see how different the distribution in the galaxy will look like. Yes, I think I agree with you here that there might be some differences.
Okay. Is there anyone else? Yeah, sorry, go ahead. Sorry, Sankha.
Okay. No, I'm just asking. It was very nice idea. So yes, I'll think about it and maybe we can talk later probably.
Yeah. Is there anyone else who wants to discuss any more with Sankha? Or any other questions? Okay. Then anyway, so great. Thanks a lot, Sankha, and thanks for staying behind for a few more.
No, thank you. It was my pleasure, and thank you for asking me to give this talk. It was very nice.
Great. Okay, so hopefully we'll see you in the next session after this. I don't know, the timings may or may not work out for you.
Okay, surely.
But certainly come in for Patrick's talk too, because
surely, yes. I usually follow it sometimes from YouTube. It's much easier from there.
Oh,
so,
okay.
yes.
All right then.
Okay, great. Yeah. Thank you.